Hi there, hopefully this video finds you well and it's a good review of what a titration curve is. So we've done many examples of titrations up until this point and we've provided quite a few links in previous examples that you can see one done or you've seen one done live. So one of the purposes of a titration is to determine the unknown concentration, which we've done previously in parts A and B. A second purpose of a titration is to track the pH change over the course of a reaction as a titration happens. So remember that a titration is a neutralization reaction, so the pH is constantly changing. So the definition of a pH curve is listed here. It's where the pH of the solution is plotted against the volume of the standard solution that has been added. Okay, so your axes are pH and volume of solution. In general, we can sketch it like this: the pH and the volume of the titrant. Right. So as the titrant is added, the pH will either increase or decrease depending on if it's an acid or a base or not. The curve that results shows how the pH changes very quickly in the middle region. It can give us clues as to what the identity of the acid or base is and what the pH at the equivalence point is. So to generate a proper pH curve, at least 10 to 12 different calculations need to be made of the pH at different times during the reaction. Now that's unfeasible by hand, and usually we'll use sensors that collect that data to generate usually about 1 to 2 readings per second. So we'll be in the 1 to 200 calculation range that are automatically done for us. But when we're doing this by hand and understanding what happens, there are 5 repeated regions of a titration curve. And in a titration, there are stages that occur. So we'll identify what those are. Number 1, the first calculation we'll always do is the pH of the solution before anything is added. This means that there's only the analyte, or another word for that is the sample. So if we do a quick sketch of a titration setup on our ring stand with our Erlenmeyer flask and our burette, the titrant is what's in the burette at the top, and the sample is in the Erlenmeyer flask. Now you'll also see that called the analyte, because that's what's being analyzed. So at the beginning, we're only going to calculate the pH based on what's present in that sample. So that would be like on the curve below when no titrant is added. Stage 2 is anywhere between the beginning and the equivalence point. So that's generally in this area here. At this point, we have a mixture of analyte. We'll just erase that. We'll say analyte plus titrant is present at this point because we've added some, right? And you can see that the pH starts to change. Then you have this vertical region of the graph, and that represents the equivalence point, or stage 3. So where the pH changes rapidly, the middle of that point will tell us the pH at the equivalence point. Stage 4 is just after the equivalence point, so we can see how far down that graph will actually go. At this point, you have both the titrant and the analyte as well. Sorry, at this point you only have the titrant because the analyte has been neutralized. And then lastly, point 5 will be some point further on when the pH is no longer changing. So those 5 regions describe what a titration curve looks like. And if we look at the examples below here, they cover every scenario. So we'll call these A, B, C, and D. So scenario A, if you look at it, it's the strong acid and the strong base. The equivalence point happens when the pH is at 7, and that's when they're neutralized. In scenario B, we have a weak acid and a strong base. So if you look at the beginning of the curve, the pH is high before any titrant is added. So I want you to think and pause and ask yourself, what's the sample and what's the titrant if the pH starts off high? Once you've thought about that, because the pH is high and the pH is being measured of the sample, that means the strong base is the sample and the weak acid is being used as the titrant. Now if we look at the middle region here, and we draw a line across, notice that the pH is above 7 for this type of titration. That's important to understand. Scenario C is the opposite. Again, we're starting with a weak base because the pH is above 7, but it's not as high as graph B. So that means the base was weak as the sample and a strong acid was added in. If we look at the vertical region here, the equivalence point, that third stage, when the moles of acid equal the moles of base, right, we'll just refresh that here. Okay, we notice that it's below 7. And then lastly, we avoid scenario D because it involves weak acids and weak bases. And you can see that the equivalence point is very hard to determine in this case. Okay, it can be above or below 7 depending on what the species are. But we avoid this because the titrant, which goes in the burette, and again, the burette is up here, okay, we know what that species is and we choose it. So we should avoid choosing a weak base because it introduces equilibrium and error. So the titrant should always be a strong species and the sample can be anything we're trying to analyze. Now if we look here, we're going to identify a pattern. All right, and we'll notice that based on the type of substances in the titration, the pH at the equivalence point changes. So it's 7 when it's a strong acid and a strong base. It's above 7 with a weak acid and a strong base, below 7 for a strong acid and a strong base, and we'll ignore scenario C here. So again, pause and try to determine the pattern based on what's involved in the pH at the equivalence point. And once you've done that, you should notice that both are strong and the pH is 7. In scenario B, the base is strong and the pH is above 7. Scenario C, the acid is strong and the pH is below 7. So in general, what we can say is that the strong species will determine the pH at the equivalence point. And that's a very important property. If they're both strong, then the pH will be 7 because they'll be equal to each other. And this is based on the properties of the salt that gets produced. And you can review the lesson titled Acidic and Basic Salts for more information on that. So these pH curves give us a lot of information about what happened, what was where, and what was being determined. So a couple of examples. I'd like you to pause the video and try these as I take each one up. Okay, and if you come back now and you've tried them, let's review. So for this one, remember that the analyte is in the Erlenmeyer flask and the titrant is in the burette at the top. The pH is measured for the analyte. Okay? So a strong acid analyte is neutralized with a strong base titrant. So if I draw a graph, I'll be drawing pH curves here. We have the pH and we'll mark off 7 because we're sketching it. And we've got the volume of NaOH in this case. So because we're starting with a strong acid, we start with a very low pH. Okay? Both are strong, which means the equivalence point will be at 7. Right? And because the titrant is strong when it's the only species present, it'll be fairly high on the pH scale. So what we'll notice is the S-shaped curve with a sharp vertical region and a general shape like that. Okay, we start off with an acid, we end with a base, and the equivalence point is at 7 in this case, because they're both strong. Now in this scenario here, we have our axis of pH, we'll mark off 7. Okay, and this time the volume of the titrant is a strong base, so it's NaOH again. Now the analyte in this case is acetic acid, which is a weak acid based on its Ka value. So our previous acid started at the bottom. This one should be up a little bit higher because its pH won't be as low. Right, and the reason for that is weak acids don't ionize as much. Now, because we have a weak and a strong species, the pH at the equivalence point is going to be above 7 because the titrant is strong, and it'll have a high ending pH. Now, there's a little tail to start it off. We saw an example of why that is. Okay, and the region is less vertical here when there's a weak species involved, and that has to do with the fact that it forms an equilibrium. So notice the difference in the curves. Less vertical middle region, pH above 7, and a thicker tail to begin, which is right over here. So let's draw another scenario here. This time we have a strong base analyte with a strong acid titrant. So the titrant goes at the bottom because that's what's being added and its volume changes. The analyte's volume is constant throughout. So in this case we have HCl. So we start with the strong base, which has a high initial pH. Both are strong, so the pH is 7 at the equivalence point. And at the end, when there's only titrant present, the pH will be fairly low because it's a strong species as well. Okay, so again, with strong species, we have very dramatic changes, fairly level, sharp vertical drop, and then it levels out again. For a weak base analyte, if we draw this here, a pH of 7, and our titrant is HCl again. So a weak base has a high pH, but not as high as a strong base, right? The only strong species is the acid, so the pH will be below 7 at the equivalence point, and it'll be fairly low when the reaction is done. So weak species have a dramatic tail. They're a little more sloped, not as vertical, and they end off similar. So you can see the differences between the curves there. So the graph depends on what's present and what's being analyzed. So for homework, we'll want to review what that is. There's some information that you can review about indicators on your own. We'll save that for another time. But basically, to choose an indicator, and this is the important part here, we choose an indicator that changes color at the equivalence point, or whose color change occurs within the range of the equivalence point. Okay, so we'll save that for some personal reading, as well as the rest of that there and the theory of the acid-base indicator. We're going to stop by focusing on the titration curve. So hopefully that helped clear up the properties of it and how to interpret the sketches and the values.